In this lecture, we're going to go over how to complete the first worksheet for the Unit 4 hypothesis testing. So 4-1-1, Intro to Hypothesis Testing. Go ahead and download the 4-1-1 Basics of Hypothesis Testing worksheet, and we're going to look through that. And so right here, you'll notice it's got some good information on how to access the OpenStax textbook. If you click on this, you can look through the introduction with null and alternative hypothesis. This is all really great information. And then so there's videos that you can look at in here, but right now I'm updating some of those videos. So I'll update those links as I make these. So the different videos go through what alpha is, so on and so forth. And as you read through this worksheet, you'll see a lot of the information. But the big thing about right here as we get started, question about type 1 error significance, alpha level. You can watch a lot of the other lectures that go over that. But if you want to be 95% confident in your results, your alpha level is going to be 0.05. If your alpha level is 0.01, what is the level of significance? This is just showing you that these words are all the exact same thing. So just be aware of that. And so going through this worksheet, if you have a group of doctors deciding whether or not to perform an operation, suppose the null hypothesis is the surgical procedure will go well. So that's saying, hey, there's going to be no difference, between, a surgery going well, or, the opposite of it, which is it won't go well. The type 1 error and type 2 error. Type 1 error is saying that there is a difference when there really is not, and type 2 error is saying there is not a difference when there really is. And so type 1 error, would say, hey, there is a difference. In other words, the surgical procedure will not go well when it really does. And type 2 error is saying the surgical procedure will not go, or will go well when it really does not. So yeah, and then let's see here, which of the error has a greater consequence. So go over that and figure out which one has a greater consequence, type 1 or type 2 error. Then there's some working through this watermelon problem. But we're going to look at this right now. Okay, so you tested a total of 30 cars with rubber wheels compared to the average track time of cars, rubber wheels, and compared the average track time of cars with rubber wheels to the average track time of all cars. The known information from the population of all cars is an average track time of 3.45 seconds with a population standard deviation of 0.2. From the sample of 30 cars, the average track time was 3.8 seconds. With a chance of type 1 error of 0.05, can I be confident that the cars with rubber wheels have greater track times than the average track time of all cars? So first thing that we've got to do is we're going to look at, what do I want to know? What's the research question? So research question is basically what we have right here. Do cars with rubber wheels have greater track times than the average track times of all cars? Average track time. So what we're doing is we are comparing the average track time of cars with rubber wheels to the average track time of all cars. So we're comparing a subpopulation to a larger population. And so we've got, the subpopulation, which, let's see here. Do I have a car with rubber wheels? I do have a car with rubber wheels. So let's see here. Stop sharing. So I've got two cars here. I've got a car with rubber wheels and I've got a car that does not have rubber wheels. And you're like, oh, it's a Jeep. Of course it's going to have slower time. But I could put it, like this. Hey, this also has rubber wheels. And this does not have rubber wheels. Let's see here. Do I have other cars that don't have rubber wheels? Yeah. This car does not have rubber wheels. This car does have rubber wheels. The question is which one will have a longer track time if I put them down the track? Which one will take longer to get down to the end of the track? This one also does not have rubber wheels. So there's a lot of different cars. It's not just whether or not they look fast or slow or whatever. It's do they have rubber wheels or not? And what we're doing is we're comparing the cars with rubber wheels to the entire population. So that means that's still including all the cars with rubber wheels as well. And so yeah, let's share the screen again. Okay, so let's see here. We're looking at the research question. So what is the null and alternative hypothesis? First thing that I want to know, is this a one-tailed test, two-tailed test? What is this? There's three words that I want to look for. Okay, the three words that I want to look for are greater, less, and different. Okay, when I see the word greater, what that's going to mean is it's an upper tail test. And I'm very intentional with my questions to make it so that you have something similar to greater. So you might see like greater, more, longer, something to that effect. Something that indicates a higher number. Okay. And then down here, less, you're going to have a lower tail test. Lower is also known as a left tail. So you can do upper or right tail test, lower or left tail test. And so you're going to have less, fewer, and different words that indicate a lower number. Okay. So, and then different, you're going to say, are they just different? And in that case, we don't know whether or not the cars with rubber wheels are going to have a longer or shorter track time. We just are wondering, are they different? And so that's the case with that. Let's see here. Greater, less than. So what we have right here is we have greater, and so this is going to be an upper tail. And so when we put together our null and our alternative hypothesis, the alternative hypothesis is going to say, hey, the cars with rubber wheels are going to be greater than the average of all cars. And so what we have here, and I really should have put a blank right here, but this blank right here, 3.45, this is the average of all cars. And so what we're doing is we are comparing the average of the cars with rubber wheels, and let me zoom in there a little bit. The average, I just want these to go away. Okay. The average time of cars with rubber wheels compared to the average of the entire population. And so the average finish time of cars with rubber wheels for the null hypothesis. So the null hypothesis is going to say there is no difference. There is no difference between the cars with plastic wheels, or sorry, the cars with rubber wheels and the entire population. And so that's what we're saying. We're saying not only is there is no difference, but there either is no difference or it's the opposite of what you think it's going to be. And so we've got right here, the average finish time of cars with rubber wheels is less than, or sorry, is less than or equal to the average finish time of all cars. So we think that it's going to be greater than. So the null hypothesis saying that there is no difference says it's going to be less than or equal to. less than or equal to. Okay, and then right here we have the alternative hypothesis, which is what we think is probably going to happen. So we're always testing the null hypothesis, but this alternative hypothesis, we notice that this symbol is always pointing towards the tail of the test. So if you look at, hey, it's pointing towards the right tail or towards the upper tail, but the average time for cars with rubber wheels is greater than 3.45, or the average time for all cars. So the average finish time for cars with rubber wheels is greater than the average time finish time for all cars. So what is the level of significance? Let's go right up here, the level of significance. And you'll notice, so I'm going to highlight a few things here. So the known information from the population of all cars. All cars is the average track time of 3.45 seconds with a population standard deviation of 2.2 from a sample of 30 cars. The average track time was 3.8 seconds. Type 1 error of 0.05. Okay, and so this is some of the information that I have. And so I'm going to come right down here and it says, what's the level of significance? That's the same as the chance of type 1 error. Okay, so 0.05. What is the level of significance? 0.05. The probability of saying the average finish time of cars with rubber wheels is higher, but there really actually is not. So in other words, if I were to run 100 of these tests, 5 out of 100 of the tests will, even if they are the same. So even if there are no differences between the cars with plastic wheels and the cars with rubber wheels, 5 out of 100 tests would say that there is a difference. If I had a level of significance of 0.01, 1 out of 100 tests would say that there's a difference. And if I had a level of significance of 0.1, 10 out of 100 tests would say that there's a difference. So what's the appropriate test statistic? The appropriate test statistic is based on one thing, really. The fact that we have the population standard deviation. Because we have the population standard deviation, we are going to use the Z statistic. So we use the Z statistic because we have the population standard deviation. So now the question is what is the critical value? The critical value, we're going to pull up something and I'm going to share my screen. Let's see here. Let's go here. I want you guys to download something. We're going to go to Unit 4. We're going to go to printable resources and it says critical values diagram. And I actually just updated this, so I'm pretty stoked about this. It has a critical values diagram for t-scores and z-scores. Okay, and the critical values diagram, there's a few things that you need. For the z-score, with which that's what we have, we need the tail of the test and we need the alpha level. Tail of the test, alpha level, tail of the test, alpha level. And then for the two-tail, you also need the degrees of freedom. Okay, and so we're going to come right here and let's look at this. So what is the critical value? So the couple things that we need based on the alpha of 0.05 and it is a right tail test. And we are using a Z statistic. Okay, so these are really the three things, I guess. Alpha of 0.05, right tail test, Z statistic gives us our critical value. Okay, so the critical value, what it is we're about to run a Z test, and the critical value is, let's see, get rid of that. The critical value is a delineating point of whether or not we reject or fail to reject the null hypothesis. So right here, we're running an upper tail test with an alpha of 0.05, and so the critical value is going to be 1.645. Okay, so 1.645 is the critical value, and I'm going to put that right here, 1.645. And based on that, we are going to make a decision rule. Now, if I had a t value, I would put, this is how I would do it right here. Okay, I would have an alpha of 0.05. I would have 29 degrees of freedom, because there's 30 minus 1. And then I would do, it stands for absolute value. Oh, there should be a parentheses at the end of here too. But absolute value t dot inverse 0.05 with 0.29, or with 29 degrees of freedom, which would give me the t critical value of 1.699. So what is the decision rule? The decision rule is if, and this is very important here, the way that we're going to write this, it says z calc. We're going to be comparing z calc, because just in a minute we're going to calculate the z calculated value. Okay, if z calc is less than or equal to 1.645, we're going to fail to reject the null hypothesis. Similarly, if z calc is greater than 1.645, we're going to reject the null hypothesis. Let's get a visual of this really quick. Okay, I'm going to come down to the last page. Okay, and this right here represents the distribution of the population. This distribution represents the population distribution of all track times. When we calculate the z-score, the z-calc score of cars with rubber wheels, you're comparing that z-calc to all track times. Okay, so we're going to come right up here, and we're going to put this right here because it's an upper tail test. And so we've got a z critical value. Let's just get rid of this. Z crit of 1.645. Now, what's the z calculated value? That's a great question, because we want to know this z calculated value, whatever the z calculated value is, it's either going to be over here or it's going to be over here. If it's in this area, if it's in the area of green over on the right-hand side, you're going to reject the null hypothesis. So we're about to calculate the z calculated value. And so depending on where the z calculated value is, if it's over here, you fail to reject the null hypothesis, but if it's over here, you reject it. So this is also referred to as the region of rejection. The region of rejection for a right-tailed test is in the right tail, or for an upper tail test is in the right tail. So let's calculate the test statistic. How to calculate, by the way, yeah, I have what is the p-value. We'll get to that in just a minute. So what is the value of the test statistic? So we're going to calculate that right here. And we're just going to put this into Excel in just a second. But what this is this is the sampling error divided by standard error. Okay. So we've got the sampling error divided by the standard error. So I took 3.8 seconds minus 3.45. That's the sampling error. And then the standard error is the standard deviation divided by the square root of the sample size. Okay, so we have that all right here, and we're going to put this into Excel. Let's go to Excel. Okay, and then I've got to put a close parentheses right there. And that gives us a z calculated value of 9.585, which is very large. So we're going to put this 9.585 And the only difference is I put divided by square root. Okay, so that's how you do that in Excel. So 9.585 is um the Z value, the Z calculated value to be more specific. So this is a very large Z calculated value. And so it's probably going to be pretty unlikely. And so in order to determine how likely or unlikely it is, we need to calculate the p-value. So we already determined, the critical value. The critical value is saying, hey, we determined beforehand what that threshold is, how significant it needs to be in order for us to uh say that it's actually different. But the p-value is a little different. It says, hey, we got the result. Now, how likely is it, the result that we got, how likely is it that we got that? And so that's what the p-value is. And so the p-value, there's three different ways to calculate the p-value. And in order to calculate the p-value, you're either going to do it for a one-tailed test, one tail lower, one tail upper, or for a two-tail test. Same thing over here, one tail upper, one tail lower, two-tail test. Except this should not be, this should be t dot dist. Let's see here, equals t dot, let me show you how to do this really quick with t dot dist. What I had in there was for calculating the critical values. So equals t dot dist, and then you put the z value in of 9.585. Then you put the degrees of freedom, 29, and then you put true. Okay, and that right there is for an upper tail. Whoops. Lower 2. So equals t dot dist, dot. Sorry, this right here was for a lower tail test. Gosh, why am I messing things up? Okay, right tail, 9.585, 29, upper, lower. Okay, and I'll show you the formulas, show formulas. There we go. And then equals t dot dist dot 2t, then 9.585 and 29. Okay, so that's how you get the probability with a t-test, but we're not doing a t-test. I just wanted to show that because I messed this up. And I'll fix that. Let's see here. T dot dist. Let's just do this really quick. Okay. And then upper. And then lower. Or sorry, two-tailed. And so I'll update that and upload it as well. But that's how you would do it for that. Okay, so formulas, show formulas. Okay, so when it has something like this, what this really means is there's 11 zeros, and then there is this 855. Same thing here, there's 10 zeros, and then there's this 1 7. and then this right here is just 1. That's because it's a lower tail test. In other words, it's complicated, but essentially it's 1 minus this, and so the way that they put it is just 1. If you were to go like let's see here, page home, let's see here, there we go, there we go. So you notice the probability of actually getting it is 99.99999999999144443. And so it says 1, but it's not actually 1, it's just rounded to 1. Same thing with this. If you can keep going all the way down. Same thing with this. It's times 10 to the, so there's 0.000000000000171. So that's the actual probability, but we don't put that. What we do is probability is less than 0.001 when we have something like this. And then we also put like right here, we wouldn't put any probability at all. We would just say we reject or we fail to reject the null hypothesis. Okay, but looking at the z-value, it's a very similar thing. So we do right here the p-value for, so this right here is for t-values, which we're not using this time, but for z-values, we're going to do equals norm, let's do this, lower, equals norm dot s dot dist, and then we put the z-value 9.585, and then we put true, and then so it gives you 1, and then we do equals 1 minus norm dot s dot dist, and then you put the z-value again, 9.585, true. And then for the two-tailed test, you take whichever one of these two is less than 0, or sorry, less than 0.5, equals the upper multiplied by 2, and that's what you get. And so you're like, that doesn't make much sense at all. And the reason why is because that z-value is so big. Let's see here, can we even get to it? Yeah, it's just calculating it as 0 because it's so unlikely with a z-value. But eventually there should be yeah, I think it's just deciding to calculate it as 0. There should be some numbers down here. But it should be something to the negative 64th or whatever, if you were to keep on going. And so the probability of it's so low, once again, all that we would do is put p is less than 0.001, and same thing right here. And then right here, you just wouldn't put anything. So what does that p is less than 0.001 mean? Okay, let's figure that out. So we put p is less than 0.001. So this is the probability of getting this result, assuming that both the sample and the population are the same before you ever test. So let's come back down here again, and we're going to put z-calc is 9.585. So the probability of getting this is very low. The reason why is because it's all the way down here. So if you were to keep going like this, and yeah, it would be 9.585. Let's see here. And the probability of getting this 9.585 is so minuscule that it's virtually 0. But we can't say that it's 0 we have to say it's virtually zero or virtually non-existent. In other words, the probability of getting it is so low that we're going to say it's going to be less than 1 out of 1,000 times or less than 1 out of 10,000 times that we would randomly get this. Um, so what is the final decision? Reject the null hypothesis because the z-value of 9.585 is greater than the critical value of 1.645. And so we are right here 99.9% confident that the average finish time with cars with rubber wheels is greater than the average finish time with all cars. Now, technically, you could put 99.999 because what you're basically doing is you're corresponding it with this. But I would say only go to the tens or the hundredths place when you're doing something like this, because you don't want to overestimate how confident you are. If you overestimate how confident you are, people are going to look at it and you're going to be like, hey, did you really do everything correctly? And the truth of the matter is there's a few things that we should have done a little bit differently when we ran this test. If we really want to be able to say that we have that much confidence. And so if you really want to have that much confidence, you have to do a lot more work into really saying, hey, we checked and we corrected the data, we cleaned it up, we did these different transformations. So it's really good to just put p is less than 0.001, and then we are 99.9 or 99.99% confident. And I wouldn't go any bit further than that. And so yeah, the distribution right here shows you that this is definitely in the region of rejection. So we should reject the null hypothesis and say, hey, we are 99.9% confident that the average finish time of cars with rubber wheels is greater than the average finish time of all cars. And that's how we do that first worksheet. And yeah.